All right, so we're looking at exponential functions. So definition of your exponential function, f of x is equal to b to the x power, or y is equal to b to the x power. But the main thing we recognize here is that our variable is the exponent. So when that's the case, that is your exponential situation or your exponential function when your variable is in the exponent position. Excuse me. So this is not b times x. This is b to the x power. Then at the bottom of that, where b is a positive constant other than 1, and x is any real number. All right. So we want to graph 2 to the x power. And let's say they told us to graph using 3 to negative 3 as our integers. Then you would plug them in accordingly. So notice if x is 3, that means we're looking at 2 to the third power, which is 8. Then 2 to the second power, which is 4. 2 to the first power is 2. And then 2 to the 0 power is 1. So don't forget anything to the 0 power is going to be 1 for us. And then don't forget how your negative exponents work. 2 to the negative first power means I will bring it down to the denominator in order to execute. So that's 1 over 2. Then 2 to the negative second, 1 over 2 to the second power, which is 1/4. Then 1 to the 1 over 2 to the third power, which would be 1/8. So that's how we got our values of our chart. So it's the same thing that we normally do, it's just that we're dealing with exponents. So before we go any further, make sure we're okay. All right, and then if you go to graph, it will look like this down here. So as you go to the right, it continues to grow very quickly, 2 to the fourth power, be 16 and so on. And that's what it means for something to grow exponentially. It grows very, very fast. All right, any questions on that? All right. Natural base E. So E in mathematics, scientifically, when you look at your scientific calculators, if you see E, it actually has a value. There's an application there. So E to the first power is 2.7182818 with a run-on decimal. So there is value there. It's not a just random variable. That's your natural base E, and that's going to come back up in a little bit. But just so you know what it is when you see it. So that's going to take us into compound interest. Hold on 1 second. All right. Sorry about that. So compound interest, we have n compounding periods per year. Sorry about that. I had a sneeze. All right. So A is going to be equal to P times 1 plus R over N raised to the N times T power. And some of you have seen this before. So when you're talking about, deposits into a bank account, loans, money taken out, being applied over a certain amount of years with a certain rate, that's what we're looking at here. Continuous compounding would be A equal to P times E to the R times T power, or RT power. So continuous compounding carries on a different formula altogether. And so when you're talking about compounding periods, talking about when you go into a bank or look at a bank and how many times they hit your account with the interest application. So this is what P, R, T, N, and A represent for us. All right, so P represents your principal, which is deposit or loan. R is your rate. Don't forget to convert it to decimal before you calculate. T is your time in years. N is the number of compounding periods per year. A is your future value. In other words, how much is in the account after a certain amount of years.
Professor Tucker?
Yep.
Sorry, I came in late. Is it possible I can see how much I've missed?
Yeah, hold on 1 second. All right. Questions before I move up a little. All right, so it's this much right here. So yeah, it's a little bit as far as notes are concerned. So it's just I'll double back, before everything's said and done, and let you get that.
All right, all right.
Yep, yep. All right. So when we talk about compounding periods, what our N will be, there will be key phrases or key words that will let us know what N will represent numerically. Annually means that N is equal to 1, semi-annually, N is equal to 2, monthly, N is equal to 12, quarterly, N is equal to 4, weekly, N is equal to 52, and daily, N is equal to 360. And not 365, we're using 360, and that's called Banker's rule. All right. But it's still holding on to green. All right. So you decide to invest $8,000 for 6 years and have a choice between two accounts. The first pays 7% per year, compounded monthly. The second pays 6.85% per year, compounded continuously. Which is the better investment? So I'll give you guys a chance to write that out. All right. So once again, you decide to invest $8,000 for 6 years and have a choice between two accounts. The first pays 7% per year, compounded monthly. The second pays 6.85% per year, compounded continuously. Which is the better investment? So looking at the information that we have, write down with the green. All right. Right now, given information for the first account, $8,000, 7% interest, convert that to a decimal, that's 0.07. Then we're looking at 6 years and compounded monthly, which is 12. And you plug it into that first formula, A is equal to P times 1 plus R over N raised to the N times T power. So that's this formula right here. Make sure you know how to use your calculator. If you do not, always feel free to get with me on it so we can see what we can do to help you out. Every calculator can be a little different. If you got a calculator that can just type it in, with the parentheses and everything like that, you be typing in just like that, then that will be the answer that you get. All right, so before we look at the second account, questions on what we did there. All right, looking at the next one. So it's still $8,000 that we're depositing, but this time the rate is 6.85%. Still going to be 6 years, but we're compounding continuously. So we're going to use that different formula. The second formula is down bottom. The second formula that was given. So it's P times E to the R times T power. And that's what we did down here. 8,000 times E to the 0.0685 times 6. And that will give us $12,066.60. So we see that the better investment with $12,000, with $12,160.84 is the better investment. So it's better to use the monthly with the rate of 7% than to compound continuously with a rate of 6.85%. All right, questions on anything so far? Make sure we're all right. All right, so we good to go? Everybody straight? All right, so that's all 4.1 holds you responsible for. Make sure you know how to graph and then using the calculator to use these formulas. So make sure you try it out, see if you have any problems with it. Let's look at 4.2, logarithmic functions. So for when x is positive, that's what this means right here. When x is greater than 0, b is positive as well. And also b cannot be equal to 1. Our logarithmic function will be represented in this way. Y equal to log base b of x. And that's also equivalent to the equation b to the y is equal to x. So both of these are equivalent statements. And so you'll see how we can translate between the two in a second. And it just says in the red, the function f of x equal to log base b of x is the logarithmic function with base b. So just driving that point home. All right. So log form is y equal to log base b of x. Exponential form b to the y power is equal to x. So notice here that our base is always going to be the same, whether you have your b being your base being the base of the log or base of your exponent. So when you go translating between the two, your base will always be the same. But what I always point out is that if x is next to b in the log form, x will not be beside b in your exponential form. So that's the kind of way I look at it. So I always start off with my base, and then whatever's next to b in one representation would not be next to b in the other. And so when we put numbers on it, it may look a little better, but you'll see exactly what I'm saying. All right. All right, so we're talking about the next two exercises, how to go or translate between the two, going from log form to exponential form or exponential form to log form. These are the type of skills that will help you out when you talk about, working out problems in calculus. How can you manipulate problems in order to get an answer? So we have 2 is equal to log base 5 of x. Notice I start off with my base. Base is 5, so my 5 will always be my base. Notice it is beside x here. So when I go to the next relationship, the exponential relationship, I will not have x beside my 5. It will be 2, and then x will be on the other side. So that's 5 to the second power equal to x. All right, so you always start off with your base. Your base is always going to be the constant throughout both relationships. And we look at the next one, log base 3 of 7 is equal to y. If 3 is my base here, 3 is going to be my base here. All right. So what's going to be my exponent? It cannot be the 7 because the 7 is right beside the 3 in my log form. So that means I have to have y as my exponent. Then 7 will be on the other side of the equal sign. All right, same thing for the last one. My base is a, and my exponent should be 3 with 64 on the other side of the equation. All right, questions before we go to the next one? All right, so in the next one, we're going the other way. We have our exponential form, and we're going to go and write it in log form. So our base is 12 here, so it needs to be the base of my log. And the 2 is next to the base, next to the 12 in the first relationship. So that means x needs to be here next to the 12 when I deal with my log. And then 2 will be on the other side of the equation. Same thing with b when we look at b cubed equal to 8. B is my base. The 3 is next to the base here. So that means it would not be next to the base over here. So that'll be 8 log base b of 8 equal to 3. And then for that last one, that's going to be a log base e of 9 equal to y. All right, questions on any of those? All right, so we have some general properties of our logs. So no matter what your bases are, these properties will hold true. So log base b of 1, the log of 1, no matter what the base is going to be 0. Then log base b of b. And if we look at the rules for 2 and 3, they're very similar. They emphasize the same relationship. So in other words, if you have log base b of b, that's going to cancel out or reduce down to 1. But the main reason is because our exponent is 1. But log base b of b to the x will reduce down to x because our exponent is x. So basically, if you have the same base on your log applied to a number that has an exponent, or just a regular number that is the same number, that will reduce down to whatever the exponent is. And then for number 4, if you have a number raised to the log base b of x, a b, let me see how I want to say it, number raised to the log base of that same number of x. And notice that this part cancels and leave you with just the x. Yeah, most definitely. And so over here in the purple is just many examples of what's going on. Just put numbers on it. Log base 5 of 1 is equal to 0. Log base 7 of 7 is equal to 1. Log base 4 of 4 to the 5th power is equal to 5. Once again, that part cancels, leaving you with just the 5. And then 8, log base 8 of 9. That part will cancel, leaving you with just the 9. All right. Any questions? Any questions? All right. Common log. There are 2 logs that are already programmed in your calculator. If you have a scientific calculator, the first one is a common log. That's log base 10. So whenever you're dealing with logs and you don't see, how do I say it? You don't see a log base, then they assume you know that there's a 10 there. So it's always assumed that there's a 10 there if you don't see nothing there at all. All right. And that's a little common log, log base 10. All right. So those four properties applied to the common log. Log of 1 is equal to 0. Log of 10 is equal to 1, because remember, you're assuming there's a 10 there for the base. Log of 10 to the x is equal to x, and then 10 to the log of x is equal to x. All right. The next one is natural log. They go to natural exponent, natural function of e comes back up. It's natural log. So log base e of x is going to be ln of x. So when you see ln, you're going to always know, or they're going to always assume that you know that the base is e. All right. So then those four properties apply to the natural log. Ln of 1 is equal to 0. Ln of e is equal to 1. Ln of e to the x is going to reduce down to x, and then e to the natural log of x is equal to x. Any questions? Any questions? All right. Let me erase some of this stuff so we can walk through it. All right, so we have log of 100. So don't forget that's your common log. So if you can manipulate the problem in some way to deal with tens, that would be in your best interest, because we know we have a log base 10 here if you don't see anything at all. So we can rewrite that 100 as 10 squared. And now that we have log base 10 of 10 squared, we know that that part will cancel and leave us with just 2. All right. Next one, 10 to the log of 33. That 10 and that log will cancel and leave you with just 33. Here we have natural log, so that means our base is e. And so it would be to our benefit to rewrite this without being an exponent and without being a fraction, excuse me. So we'll write it as e to the negative 6. So don't forget how your negative exponents work. If it's positive and it's our denominator, we can rewrite that by bringing it up top and using a negative exponent. And now natural log of e will cancel, leaving us with just negative 6. Next one, e to the natural log of 75. So this will cancel, leaving you with just 75. All right, any problems so far? All right, so the next one we have log base 3 of log base 7 of 7. So we do what's in the parentheses first. That'll be log base 3 of 1. So log base 7 of 7 will reduce down to 1. And log of 1, any log of 1 will give you just 0. All right, any problems with that? All right, so the next one we have log base 5 of log base 2 of 32. So when you look at what we have here, you want to do what's inside of the parentheses first. And see that we have log base 2. So here it would be in your best interest to see if you can manipulate or change 32 into a number with the base of 2. And we can do that because 32 is 2 to the 5th power. So I'll rewrite that as log base 2 of 2 to the 5th power. That reduces down to just 5. Then log base 5 of 5 is 1. All right, questions, any questions?
Professor Tucker,
Yep.
what's the purpose of log?
They have applications like exponential, when you talk about growth and decay and logs, I think they're along the same lines, but they have applications when you start talking about word problems and stuff. But I know most definitely exponential, what comes to mind is growth and decay of certain things. You gotta think about log though. Probably no engineering use logs. Um, Let me get some specific applications, but I know once they're introduced mathematically, you'll always be using them. So you're talking about calculus, trig, or whatever, they keep popping up. So yeah, the more you get in there, the more you'll see, the applications when you get those word problems.
So I'm going to see this in applied calculus.
Yeah, man.
Oh, Lord. Sorry for being Debbie Downer, folks. Just need to find out the purpose. Looks like,
Say again.
looks like fractions.
You said it looked like them?
Yeah, it looks like you're reducing fractions.
Well, we will use them alongside fractions. You'll see in the next section. But yep.
That's what I get from looking at it. You're trying to reduce numbers to almost fractions and canceling each other out and finding a base number.
Well, when it comes to mathematics, once you get to a certain point, it's always about manipulating the problem so that it can be to your benefit and you'll be able to do something with them. So, yep, you can look at it that way.
Thanks. I just had to interject.
Yep, not a problem. So that is it for 4.2. So the thing now for you guys is to try this stuff out and see if you get stuck and see if you have any problems with the relationships and the reducing and manipulation of the problems. And then, we can go from there. Any questions before we close out? Everybody good with 4.1.4.2?
Really, Professor? Really, Professor?
Well, some questions may not show up until you actually get in there. And I understand that.
I'm still trying to get the other chapter.
Well, we got time. We got a little time. So,
Question concerning that.
okay, what you got?
Maybe after class.
Okay. So, you guys are good. I'm good. I will see you guys next class on Monday, and we'll get into 4.3. All right.
I have a question. Can I stay after class, Professor Tucker?
Yep. All right. Let me see. Where's that button?